Hello everyone and welcome to Calculus Grade 12 classes, and today we are going to have a short online recording of a simple chapter but which is very important for our future studies, and we're talking about the dot product of two geometric vectors. And in previous chapter we discussed concept of multiplying a vector by scalar. But what would happen if we multiply two vectors by each other? And definition of the dot product of two vectors will help us with that. So the dot product for any two vectors is defined as the product of their magnitudes multiplied by the cosine of the angle between the two vectors when the two vectors are placed in a tail-to-tail position. So let's take a look at this diagram. Here you can see that we have vector AC as well as vector AB, which are truly positioned in tail to tail, and we can see that they have theta angle between them. And formula to finding the dot product of these two vectors, dot product is also known as scalar product. And because if you take a look here, all the quantities to the right hand side in these equations are scalars, because AC vector stated as its magnitude as well as vector AB. We have AC vector magnitude, AB times AB vector magnitude times cosine theta, while theta can take values in a range from 0 to 180 degrees including. So let's talk about observations about the dot product. First one, we already mentioned that result of a dot product of two vectors is going to be a scalar quantity, as you can see to the right hand side of the equality sign. So for this reason, we call it scalar product. Secondly, the dot product can take several values, particularly positive, 0, or negative values, and it's defined by the angle between two vectors. As soon as both magnitudes are positive, unless one of them is 0 magnitude, there is no other way to get zero 0 as a result of dot product if we're talking about their magnitudes. But we also have a cosine, and you have to remember that there are certain situations when cosine equals 0, when cosine function equals 0. So let's take a look at three outcomes of a dot product. So for the pair of vectors A and B, where dot product expressed as a modula of vector A times modulo of vector B, or their magnitudes, times cosine of theta, where theta takes value in the range from 0 to 180 degrees. For angles where theta is from 0 to 90 degrees, cosine function would take positive values or greater than 0, which means dot product is going to be a positive value. Important notation here that A and B vectors are non-zero vectors. If one of them is 0 vector, result is of the dot product is going to be 0. So for theta, for for angle theta to be equal 90 degree, cosine theta equals 0 degree. We have to remember this because it's table value for cosine. I'll remind you that there are several table values like 30, 45, 60, and 90 degrees, as well as 180, because cosine and sine functions are repeating themselves, they're cyclic. So in case when angle theta equals 90 degree, dot product will be equal to 0. Remember that. And for cases when angle between two vectors is from 90 degree to 180 degree, including the 180 degree, cosine function would be negative or less than 0, which brings us to conclusion that the dot product would be negative as well, because magnitude of a vector can never be negative. So cosine will define the sign of a dot product. Let's discover example number 1, just to clarify what we have just learned. Calculating the dot product of two geometric vectors. Two vectors A and B are placed tail to tail and have magnitude 3 and 5. So vector A has magnitude equals 3, and vector B has magnitude equal to 5. There is an angle of 120 degree between the vectors, so theta equals 120 degrees. So we have to calculate dot product of A and B. And let's remember, the first thing we do, we're gonna write a formula for dot product of two vectors. Vector A dot product is vector B, or scalar product, that's the way you prefer, equals A magnitude of vector A times magnitude of vector B times cosine theta. Now let's plug in the known values for us, and we're gonna see that it's equal to 3, yeah, right? Modulo of vector A 3 times 5 times cosine 120 degrees. And let's remember that if we sketch our circle for all the sine and cosine values, cosine 120 degrees starting from point 0, it will be in second quadrant. It's going to be somewhere here. This is our angle theta, 120 degrees. And cosine of 120 degrees is equal to -1/2. We could also see that as angle of we can also go in negative direction and calculate it as 240 degrees in negative direction. But anyway, we're gonna end up in the same point, and the value of cosine here is -1/2. So we're gonna plug in that value, and we now know that dot product equals is gonna be negative. So you have 3 times 5, which is 15, times -1/2, which is equal to -7.5. This is how you can evaluate the dot product for any two given vectors when you know their magnitudes and angle between them. In this particular problem, it was mentioned that vectors A and B are placed tail to tail, and it's not a coincidence because that's the way for us to define angle between those two vectors. Otherwise, when they're just randomly positioned in a space, unless you're familiar with that, how to work with vector components, it will be really hard to define angle between them. In this particular case, we're talking about geometrical vectors, Maybe we'll cover some examples a bit later with component form. Let's discover this investigation a little bit. It looks kind of interesting to me. We'll go through A, B, and C part of it. The rest I'll leave for your personal own solution. So question A, given the vector A and B, where modulo A equals 5 and B equals 8, and the angle between the vectors is 60 degrees, calculate dot product of A and B. Again, we will write a dot product formula, which is A times B equals modulo A, or magnitude of vector A times magnitude of vector B, and all together multiplied by cosine of 60 degree. And at this stage, you can refer to your digital calculator or any other device that will help you to define the cosine of this angle. As well, you can use the table values, and cosine of 60 degrees is gonna be sorry for that. And cosine of 60 degrees is 1 over 2. So 5 times 8 times 1 over 2 equals 20. We can see it here. If we simplify it, we get 4 here. 8 divided by 2. 5 times 4 is 20. So the answer is 20. Dot product equals 20. And take a notice that it's a scalar quantity at the first place. Let's move on to question B. For the vectors given in part A, calculate B times A. Okay, let's see. Will the result change if we multiply B times A? Again, I'll write down the formula. I'll have modulo B times modulo A times cosine. Again, if I multiply B by A or A by B, angle between these two vectors would not change. So I'll again multiply by cosine of 60 degree, which brings me to the same result. Look over here. I have modulo of vector B is 8 times 5, which is modulo of vector A, times 1 over 2. And again, I'll simplify it exactly the same way, and the result would be 20. Again, and this is very important notation. From this point and so on, we can say that dot product obeys properties of distributivity. So we can even rearrange position in the dot product, and it will not affect the result. As we can see in the dot product formula, it is clear that rearrangement of terms in this product would not affect the result, because we are multiplying quantities and order is not important in this case. So the vectors given in part A, calculate A times A and B times B. Based on your observation, what can you conclude about U times U for any vector U? So let me clean up this space a little bit. So vector A times A gonna be equal to modulo A times modulo A times cosine Wait, of what angle? What is the angle between these two vectors? I believe it's supposed to be 0, because if two vectors are equal, they're collinear, which means vector between them is equals to 0. This will simplify our life because cosine of 0 degrees equals to 1. So we're gonna have 5 times 1, which gives us 25. Dot product of vector A by A is 25. And what about B? Again, modulo of vector B times modulo of vector B times cosine. Again, 0 degree because vector B is collinear to itself. And we're gonna have 8 times 8, which gives us 64. Now this is our dot product, 64. And again, we can state that whenever we multiply vector by itself in the dot product, the result is going to be a square of its magnitude. I think that's a good conclusion from this one. Rest of the examples for this particular task, I would like you to solve on your own. So please refer to this page. If you have any questions, feel free to contact me anytime. And let's talk about properties of the dot product. It should also be noted that the dot product can be calculated in whichever order we choose. In other words, P times Q would be also equal to Q times P. We can notice down if we expand this in a line, equality would keep safe. We can change the order in the multiplication because the quantities in the formula are just scalars. That is numbers. And the order of multiplication does not affect the final answer. You see, now the book says, the book confirms my words because it's a multiplication, nothing getting affected. This later property is known as the commutative property. Sorry, I made a mistake, not distributive, but commutative. But we'll get to the distributive property for the dot product. Another property that proves to be quite important for both commutation and theoretical purposes is the dot product between a vector P and itself. The angle between P and itself is 0. So basically, dot product would be equal to square of a module or square of a magnitude of its own vector. And here they say that cosine of 0 degrees equal to 1. Please remember, this is very important table value. You're gonna see it a lot. Let's take a look at example number 2. In this case, we're given with the vector A, which has a modulo equals to square root of 7. And we are also given with two unit vectors, I. These are unit vectors in x-axis usually. Let's apply what we just discovered about dot product of a vector by itself. So the dot product for vector A in this case would be square root of 7 squared, which is equals to 7 itself. As question A solved, not so hard. But question B, what would happen if we multiply two unit vectors by each other? We know that the unit vector I lays along x-axis and its magnitude equals to 1. That's the definition of a unit vector. It's a vector that has magnitude equals to 1. In general, for any vector that has magnitude equals to 1, its square, the square of its magnitude would be equal to 1. So we can conclude that for any pair of unit vectors, whether it's I, j, or k unit vector, I is for x-axis, j for y-axis, k for z-axis, all the time the dot product for the unit vector by itself would be equal to 1. I hope there is no questions about this, just clarifying some facts. And another important property that the dot product follows is the distributive property. In elementary algebra, the distributive property states that if the product of p times q plus r in brackets equals p times q plus p times r, and that's pretty obvious. And we will provide that the distributive property also holds for the dot product. We will prove this geometrically below and algebraically in the next section. Okay, so theorem for the vectors p, q, and r, p times q plus r equals p times q plus p plus r. Okay, so proof as follows. P, q, and r are drawn. Let's state them. P, which is red vector, q, and r, I believe r. Let's notate them. A, e vector equals to p, I believe. What they say. Oh, actually, P for them is AF. Sorry. So vector Q is AP. And vector R is BC. So AC vector equals Q plus R. And to help visualize the dot product, lines from B and C have been run perpendicular to P. And P in this case is AF. Okay. Now let's use the definition of a dot product. Basically, Q vector times P vector would be modulo of vector Q times modulo of vector P times cosine of angle between them. And what angle is this? It's BAF. So this angle. This angle. It's going to be BAF. Okay, cosine of BAF. Let me show this angle. Move this here. If you look at this right angle triangles ABD, and use the cosine ratio, ABD, okay, cosine ratio, we know that BAD equals cosine ratio, it's adjacent divided by the hypotenuse, so AD divided by Q, which is our hypotenuse in this case, and yeah, that's what they say. Or AD which is adjacent, would be equal to Q times cosine BED. Okay, this is something. The two angles BED and BAF are identical, and so AD equals Q times cosine BAF. So we can say that BAD angle equals BAF. So we can substitute one for another. Now we will rewrite the initial formula while replacing in this particular case so this is our initial formula which we wrote previously, and let's just group up terms here, Q and cosine together. So now we can substitute it for AD. So now we can say the dot product of Q times P vectors equals AD times P by modulo. Okay, interesting. So now we also consider the vector R and P. Vector R in this case is BC. Okay. We have to consider R and P together. We translate the vector BC so that point B is moved to be coincident with point D. So basically what we did in this case, so we took this BC vector and translated it into this point. And the result, you can see it right here. This is how it looks like. That's what we get as an outcome. So keep in mind that vector should maintain its initial direction after being translated. And now let's try to write a dot product for these two vectors. Again, we'll use the same dot product formula that we just discovered, which is modulo of one vector times modulo of another vector times cosine of an angle between them. For this particular case, vectors R and P, so we're going to have modulo of R times modulo of P times cosine of an angle between them, and it's going to be CDE. And if we use trigonometric ratios again in the right triangles, we'll discover that CDE is adjacent. Cosine of CDE is adjacent side divided by hypotenuse, or in this case is going to be DE divided by R. So we can express DE as R modulo R time, or magnitude of vector R time cosine of CDE. That's kind of interesting. And now we would like to substitute it into our formula for R dot product of R and P. Now we're again going to rearrange this equality, and we're going to have modulo of R standing next to cosine of CDE. So now we can substitute both of them for DE. And it's going to be brilliant because now we have, instead of initial function, we obtain dot product of R and P equals DE times modulo P. If we use the formula for the dot product of Q plus R and P, we get the following. Let me clear all the drawing. Now by applying the formula for just directly as we see it, right? We know the dot product, so we were asked to prove Q plus R times BP. It's a dot product, and we'll write it as usual, modulo of a first term times modulo of a second term times angle between them. CAE angle. Let's take a look at the drawing. And hello, 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 hello. Yep, sorry for the inconvenience. Let's continue. I was saying that now we're gonna take a look at the angle between Q plus R and P vector. It's gonna be CAF, right? Let's take a look at what they say in the book. CAF. Yes, this is what they use. So now cosine CAE, but CAE and CAF is same angle, actually, you see. It's CAF, and this is CAE. Both are equal. So through this, we obtain that basically after writing the dot product for sum of two vectors times the vector P, using the same reasoning as before, let's express the cosine using trigonometric ratios. So cosine of CAE would be AE divided by Q plus R, because Q plus R is going to be a hypotenuse in this case, and AE would be the adjacent side. So now we can express AE as a cosine of an angle times the modulo of Q plus R. So the magnitude of these two vectors, sum of these two vectors, and then we're going to substitute it into our formula for dot product and see that again we have modulo of P times AE. And why did we do that? Now let's add up these two quantities using what we just converted our dot products into. So first one is modulo P times AE. Then we had another one where it's dot product of Q and P is AD times modulo P. And what else? We had one more. And it's supposed to be here. Sorry. Yeah, dot product of RP is DE times modulo P. And you see, we have modulo P everywhere. Modulo P, modulo P, modulo P. So adding two quantities, Q times P, but dot product plus R times P dot product. We have it here, and the other one a bit higher, but we can take a look here and we see what we get before after substituting the values. Now we can factorize it by modulo P, bring it out of brackets. Next line going to be look as follows, and AD plus DE, and you can remember from properties of addition for vectors and just lines. If you see something like this, where we start in A, go to point D, then from point D, we go to point A, result would be the first letter and the last letter, or in this case, A, E. It's pretty convenient to remember, not to hesitate. And P modulo P times AE, we know it equals Q plus R times dot product P. So we can conclude that distributive property is fulfilled for dot product. Am I right? It looks about right. We got same equality after simplifying everything. Let's take a look here. Again, let's remember this. So if we have sum in brackets, and we multiply this sum as a dot product by another vector, we can apply distributive property in order to simplify our calculations. This is really, really important property to remember, because otherwise you can get stuck in your problem solving. And I would like to conclude what we covered today. Let's talk about properties of the dot product that are really important to remember. First of all, it's commutative property, when we can rearrange the terms in the product and it won't affect the resulting value. Another thing is a distributive property. It means we can open the brackets as in usual algebra. Next one is a magnitude property, whereas dot product of a vector by itself equals magnitude of this vector squared, which is kind of obvious. We've seen why it's so, because vector multiplied by itself is collinear to itself. So angle between them equals 0 degree, and cosine of 0 degree equals 1. And you remember that in the formula for the dot product, cosine is a multiplier. Another thing is the associative property is a scalar. So again, scalar, we can move it around, don't be worried about it. We can put it at the beginning, at the end. If we multiply by it, then it's not a problem. We can multiply by scalar at any moment. You don't need to do it right away, and there is no such restrictions. So I hope today's class helped you to figure out dot product of two vectors a bit better. If you have any questions, please feel free to refer to me. I will happy to answer any of your questions. And I wish you all the best and stay safe, and see you in another class. Bye-bye.